Never seen this one before. So I'm going to start this. We'll talk about that one. It's actually introduced in this section. Who's ever seen the integral of x squared plus 1? 1 over x squared plus 1. Ah, Sean, what is that? Mark? Inverse, yep, inverse tangent. Do you know that? The integral of this, 1 over x squared plus 1. Doesn't that look close to it? But this should look new to a lot of you. So we'll talk about that last. This one's easy. What's that? All right. This requires an old technique. We've only had 3 major ones so far. This is the third one. U subs, substitution rule, integration by parts, and now partial fractions. How do you think you can get that going? A U sub will work. A U sub is going to work on the middle. We have to use a U sub. What would you let? Remember with U subs, go for that power higher by 1 thing. What are you going to let U equal? All right, so for this second part right here, maybe I can spread it out a little bit. So people over here, I'm just going to spread this out. Minus, what's this last part? 2 integral 1 over x squared plus 9, right? Just leave myself some room. You can do the same thing, so you can do your U sub. You know, unless you can do it in your head. Some students do it in their head. I'm going to let the U equal to the x squared plus 9. Oh, okay. What's du? 2x dx. I gotta knock out the x dx. So I'm gonna divide the 2 on both sides. 1/2 du must equal x dx. It's ready to substitute. The beauty is, everyone, we're gonna get this integral. This is way better than what we had originally. Long problem though, huh? I know. Well, it's one of the crazy ones. We'll get it. We'll get it. Okay. I'm going to put this back in. You got a minus 2 here. Is it okay if I put the half at the minus 2? What's minus 2 times the half?
Minus 1.
Oh, minus 1. X dx turns into a du. And you got a 1 over 2. So when that 2, just so you know, that minus 2 times that half is what made this turn into 1. Does everyone see that? If you want, you can write 2 times the half out here. I don't want to rush you on that. Sometimes you're like, how did that turn into 1? I took that negative 2, so 3 times that whole way. So what's this turn into? Minus natural log of u. Well, what was u? So we keep writing this. I keep writing this. I don't want to forget about that thing. Minus the natural log of x squared plus 9. Do I need bars? So I'm going to soften it. Yes, you can leave bars, but you'll notice the back of the book does that too. I want you to know why. Was that okay with the U sub on the second part? Right. Now this one. Well, there's 2 ways you can look at this way. The one way is there's a formula for this. All right, it's introduced in your textbook in this section. So if you're wondering, was this formula given back in Calc 1? I don't recall it. No. It got introduced in this section because situations like this emerge in a section a lot. You go, oh, that is a rational expression, isn't it? But that one's easy. What was this? Arctan of x. Well, what's another way to write that? Inverse tan plus c, right? How do you deal with situations like this? So when I'm going to put it's just a nice little integral formula. And it's for the expression, the integral of 1 over x squared plus a squared. The integral of 1 over x squared plus a squared, where a is a constant, becomes 1 over a inverse tangent x over a. Just from experience, I know students have no problem remembering this. But isn't that cool? Now, we could prove this if you want. It's not hard to prove that. You can prove it by a U sub, to be honest. You're like, I'm going to prove that. That's not a hard proof. But everyone knows A's are constants. Those A's are constant. It should work here, too. Does it work here? But this gets introduced in this section because it is a rational expression, but we're going to have to deal with that last scenario. Okay? If anybody wanted to see that proof, just let me know. Can you show me why that's happening? It's actually easy proof to use sub. Just, show that in terms of how to derive it. Okay, then, what's the A value here? A equals 3. Do the formula. So when everyone's recognizing here, I'll draw an arrow. They're like, A is not 9, but A equals 3, and I'm going to use this formula. It'll be minus 2, parentheses, and I just want to write what we just said. It would be 1/3 arctan. You'd like to write arctan or tan -1. It's up to you in terms of notation, right? How did I write it over there? I put the tan with the -1 in the superscript. I'm going to write arctan of x over 3. Because I want you to be familiar with both notations. Oh, plus a constant, huh? Look at that answer. That's the antiderivative. Again, who uses Wolfram alpha? I think it's great. Anybody else? Try that tonight. If you get a chance, just put it in there. Put in the Wolfram alpha. Look at that antiderivative. You can't make these more. Well, you can multiply 2 times a third and get what? 2/3. 2 natural log x minus 1 minus natural log x squared plus 9 minus 2/3 arctan x over 3 plus constant. Awesome. Noah.
Could you condense it by using log numbers?
You sure can. You can put that 2 up here. I love it. And then you could do what's a minus. You could do the numerator of the denominator. I think that's great. Feel free to do that. This is fine now. I know you were asking me earlier, can we leave it like that? Absolutely. But you definitely could do that. He wanted to go further. He's like, oh, I can move that up here. X minus 1/3. And then he has a minus here. So no, very good. Everyone okay with all that? Hey, look at this next scenario. It's unlike any of these problems when it's in a section because it's a rational expression. That's a rational expression too. Check out this next one. Oh, go ahead.
Saving value to the absolute value.
Oh, if you don't, it's okay. You agree there's no way in the real number system this could ever be negative for any x value? That's why. I did it because I know I'm sure you check solution manuals, the back of the book. You're going to notice I'm doing the same thing. I didn't want you to be at home going, is that a typo? So when they see that number, it's automatically positive or not good. You can still do your part. All right. And when this is like number 7. How do you deal with this? So this should kind of startle us. Oh, rational expression. Maybe U sub. U sub's not going to work. Stare at it for a while. See, it's got the markings of a partial fraction problem. You go, maybe U sub. Yeah, but when we did the U sub before, remember we let U equal to the thing in the denominator? Remember the denominator had that power higher by 1? U sub's not going to work here. U sub's not going to work. That's not integration by parts, is it? Integration by parts is stuff like what? That stuff, right? This is not it. So this is partial fractions, isn't it? But our technique's not going to work on this thing, huh? Because all I see is one lonely what? Linear factor. So I'm going to bring up an old topic, everyone. I'll watch your faces. I don't know if you like this. It could be a while. I'm talking about like a pre-calc course. Does anybody remember long division? Anybody remember long division? Now, if you've never seen it before, it's not hard. We're trying to break this into what? Partial fractions. The techniques we've learned so far isn't going to work, is it? Because we only have what? One solely linear effect. So we're just going to have to do long division. So what's long division? Oh, over here. X minus 1. Put in x squared. That's not bad, though. This will be quicker than any of the other problems we've done today, I'll tell you that. I'm going to hide that minus 1. Can you all look at that x? X times what equals x squared? So I'll put in x. Don't see I'm doing long division? Okay, x times what equals x squared? X. Now I need you to multiply this x times these two things. What's x times x minus 1? X squared minus x times negative 1? I have no long division since 5th grade. Now remember with long division, even if the last time we do it was 5th grade, we subtract down. We subtract down, okay? So what's x squared minus x squared? Good, it's gone. Here, they're gone. But there was a 0x here. There was a plus 0x. What's plus 0x? Be careful. Listen to this. Plus 0x, subtract minus x. Everyone see that? Let me see, because like we subtract down, don't we? What is a, you can write a plus 0x here if you want. What is 0x subtract a minus x? Turns into a positive x. You all see that? Need to see it again, Noah? You bet. See, what's sitting right here? We're thinking, I'll put it in yellow. There's like a plus 0x there, isn't it? That's what I'm thinking. I'm like, okay. When I take this and I subtract this, 0 minus negative 1 becomes a positive 1. Because we always subtract down. We subtract down. Now, and when we do have to do one more run here. Look at this, and look at this. Hide all the other notes. Hide this too. X times what equals x? Times a 1. Right? So x plus 1. Now you multiply that 1 to both these parts. What's 1 times x minus 1? X minus a 1. But when I need you to subtract down here. Subtract down again. What's x minus x? 0x. Good, that's fine. But be careful. No, what's sitting way down here? Just a 0. Let's 0 subtract negative 1. 0 subtract negative 1 becomes a plus 1. And they call that remainder. But then when we did it, we did it. This is what we have. They call this the remainder, but this is what we have now. It's all over. X squared over x minus 1 can be broken up into x plus 1 plus the remainder over the original, what was the original denominator? I put the remainder here, that's the remainder. Just so everyone knows, where did that come from? This is called long division. Now, could I check to see if I did this right? You could probably check it in your head. How could you add these together? That was the hard part. I went, you got it, look. Partial fractions with this x plus 1, huh? You manipulated it. Next one. That all right then? Okay.
So is that the integration, or is that just...
Oh no, but that's like the other problems we did today. 90% of the problem is just one.
Yeah.
It might even be in this case 95% because the integral of this is going to be easy.
Yeah.
But it might have been a while since you did long division. Now I want to see show of hands. Who knows synthetic division? Do you prefer that? You could have done it. But I only saw a few hands, so I won't show that today. But if you like, I get that all the time in Calc 2. You know, hey, professor, can I use synthetic division to do that? And I said, of course. You're just trying to rewrite this as, you know, and break it up so we have that partial fraction. You can check this one. But what I just did, everyone, was called long division. And if you're like, oh, I'm gonna review that, feel free to go to YouTube and just go long division, pre-cal. I mean, you'll get like the one with the what? 2 million hits site. You go, all right, this one looks pretty good. Hopefully they got a nice little 4-minute video there if you just need to review it. But that's really what's going on here. All right, so I'm going to rewrite this now. Okay, I'm going to put this back in. What replaces it? X plus 1 plus 1 over x minus 1. There's your ln, but what's that integral? You got it. No use subs or anything. Natural log of. Beautiful. Don't let long division bug you. I know, I can see something like, that's not as bad as it looks. If that's the first time you've seen it though, yeah, you can be like, what the heck? I'm Calc 2, I've never seen that before. But that's how we'd have to handle it, because the other processes would work. We'd still break that thing up. That's if I only had one sole linear factor, as we saw. Yes, you can do synthetic division, if you prefer that. That sometimes takes less writing, students prefer that. Cool. Man, they great job with this stuff. At this point, I'm just going to pass up some sheets, and we're going to work a problem from section 7.6. Now, what this is, don't let this scare you. Have you ever looked in the back of a calculus book, and they have like tables of integrals and integrals and integrals? Have you ever seen that before? I made copies of the tables for you, so you can look at this, but we're just gonna work one of these problems together. It's nothing crazy. What we're saying is we're gonna get used to how if someone gave me a formula for an integral, I could apply it and solve the actual integral. All right? So this is actually gonna be in section, I'll write it on the board, 7.6. We don't do section 7.5. And 7.6, that's what involves integration using tables. Where I can actually use, oh, there's a formula there. You're going to find it quite similar to just doing a U sub because they're going to give you the formula and we're just going to be like, all right, what am I going to let U equal to? And we'll start working the problem, okay? Hey, but I'll pass these out. You should think like, oh, I can memorize all? Yeah, how about this memorized by Monday?
Yes, sir. On a test, would you get a table like this, or would you eventually have to?
Super question. We got to talk about that one. You would either A, get this table, just bring it with you. But see, even quicker sometimes, I'm like, I don't want, I can have a student who has to search 5 minutes for which formula it is. This thing's pretty long. So I usually, like on my test, just find the one formula I'm going to use and say, use this to solve this. It's quicker. You know? Someone still was confused. I'm like, well, feel free to pull this out. I would tell them. But I'll tell you which one to use. That was a good question. That's how I do it. I say, hey, on a test, I would say, use this, I pick one of these, to solve this integral here. You go, wait, shouldn't I use the skill of recognizing it? You would recognize it somewhere. 2, 3, 4. Here we go. Hey, in fact, when I tried to put a dot by the one I wanted to use today, does everyone see I dotted number 28? Everyone see that? So I'm going to erase this. This is cool. 7.6. Using, well, they say integration. Integration using table. And you see all those integral formulas there? All right, everyone? That's the big joke, right? All right, have that memorized by what? Monday. Get out of here. No, but they're there. They're available in all those different scenarios. And thanks to all the mathematicians who derived all these, huh? Well, we're going to focus on one. Does everyone see number 28? Everyone see that number 28 here? All right. Here's my directions. Use. They've got. And when I'm writing down the formula for number 28 from that sheet, du over u squared square root u squared plus a squared. Doesn't that look like something from the trig section? It does, I know. But now we're using a formula here to solve this. They said du over u squared square root u squared plus. All over a squared u plus constant. And we're going to use that to evaluate this integral. And now I'm going to come up with a problem. Evaluate the integral. How about dx x squared square root of 9x squared plus 25. Make sure we can sketch plus. I don't want to be looking like a master. Hey, I hope you find this not too bad at all because we have a formula. We're just going to go in here and let u equal to something. We just got to recognize what to let the u equal to and what the a equal to. I say we start with the easy thing. what will A have to equal? 5. All right, does everyone agree? I'm just going over here. It looks like we're going to let A equal 5, aren't we? You get this thing going, huh? Did everyone recognize that? By the way, does everyone realize why I would use this to solve this? Does it look quite similar? That's what I mean. You could go through this thing and solve other problems in that section. This section, I think I took 4 problems as practice problems. But eventually you search through it, you'll find it. Now, what about the U? What am I going to let U equal to? You are good. Does everyone agree? So look at it carefully. We'll say, what are we going to let U equal to? Well, over here it's got U squared, 9x squared, and what's right there? U squared is x squared. Does everyone see that there? In that problem? Well, we're going to let the U equal to 3x, correct? All right. Yeah, but we'll come back to that x later on. And the reason is because this one was under the radical. This was more complicated than this. But then in the end, you and I can figure out, well, what can we replace that x with? Because eventually we will get everything in terms of u's and do the integrals. That's a really good question, everyone. You got the x squared here, but you have a 9x squared, and they wrote this as a what? U squared, U squared. So we're going to have to, we'll let U equal to 3x. But then we can manipulate this to a U sub to get the thing working. Okay? Because eventually we want to get this so that these are just the same. We'll get constants stuck out. So I'm going to start by letting U equal 3x. Okay. Now, what's du equal to? Well, why are we doing that? Because we want to get these du's out of here, right? So let's differentiate both sides with respect to x. What would that equal? 3 dx. Well, cool. There's the only thing we're going to have to add. And then I can put this what? Dx I'm going to replace with the 3dx, right? If du equals this, what's equal to that dx? 1/3 du? I just want you to glance it over. Do I have something to substitute there? What can I replace that dx with? 1/3 du. Excellent. Can I replace this radical? What can I put right there? U squared plus 5 squared, right? Is that okay with that? But here's the big challenge right there. Is when I want to get everything in terms of du. What am I going to put here? This is the big puzzle, which I think we're going to find easy to deal with. What about that x squared? What would I put there? Do you know? Well, how about this? If u equals 3x, what would x equal in terms of u? That's what we do. And when u equals 3x, right? So we can leave this as a what? A u squared? But then I'm just going to take this right here and go
1/3 squared.
Yep. I'm going to go right to the side and go, if we let u equal to 3x, what can we replace that x with? And x would just equal up u over 3, wouldn't it? And I'll put it right next to it. So I can replace this for the x, true? This will just be u squared plus 25, that's just going to be the a there, we're good there. And then dx becomes the what? The 1/3 du. Alright, it's ready. But I mean, here's my work. I just want to make sure. All this is my work. That's all we had to do to play around with this. It is now time to go back in here. We're trying to get everything in terms of u's so we can get this thing to roll into that. Right? See how it was almost close? But these were not the same earlier? Does everyone see that? We're now going to make these be the same. We're going to make them be u's. Alright, so here I go. What replaces dx? Okay, 1/3 du. I'll write it like that first so people know I put it there. What's getting squared here? U over 3. We're getting all u's though. What's in here? u squared plus, well, that just stays what? Do you want to write that as 5 squared? Maybe I'll do that. I'll write this as u squared plus 5 squared. Just so when you get ready for the formula, you know this a is just a what? A 5. That'll be a 25. That's going to be a 25. You see it coming? Can you help me rewrite that, Andrew? Like get constants out in the front. I want this to look like that. So I'll put this 1/3 out here. Great call. How about this one, everyone? He took that 1/3 out in front, but what about this one? That's 3 squared, which is 1/9, but it's a 1/9 in the denominator. Ooh, can you help me with this? 1/3 divided 1/9. What the heck is that? Right, let me lower it down so everyone sees this.
3?
Yeah, so I'm gonna write 1/3 out of 1/9 all in front of this integral. This has just got a nice du here. There's a 1 on top. This is just now a u squared, right? And a square root of u squared plus 5 squared, or 25. It is now ready. All we gotta do is plug these in and get this. This is gonna be the solution. You got all set, but you notice what we did? We went from here to get into u squared like we wanted. But a constant emerged in front. What's the constant? Is that a 3? I should write that. Then you get a 3 integral du, u squared, square root of u squared plus 5 squared. All right, what's this equal to? Now it's time. All right. Now we're going here. It's just giving us the solution. Let's type it out. What's it going to be? Write it out. Negative square root u squared plus 25 all over 25 and the letter what? U. Plus a constant, right? Now you can look and say, what did Professor Messer forget to write? I didn't want you to do this on the test. Oh, it's like just writing this. You're like, wait a minute, what's in front? The 3. Let me get that 3 in. You want me to go with the negative? Okay. Negative 3. I'll just put it right up there. I just want to put a big thing in front. Now, let me step away. Like you're about to turn in your testament. Did you finish? That's what I mean. Like they said, use this. With this, it's like a table of integrals, and we used it to solve this. This originally had what variable? So the last step, you've done this many times, you're familiar with this, then we have to resubstitute. That's all we got to do. Let's get everything back in X's. Right? That's what we do. So I'll put an equal sign, good call. Negative 3, leave that negative 3. What was u? So what's 3x squared? Okay, 9x squared plus 25 all over 25. What was u? U was just a what?
75 notes.
Oh yeah. I think it's a great idea. Can we go one more step, simplify this? Good on. Rather than leave it like this, these 3's what? Cancel out, see that? So I can write this final answer as negative square root of 9x squared plus 25 all over. Don't forget that lonely. But hey, looking at this problem, you know what else you can do? You might say, okay, I used that table to do that, but you also can play around trying the trig substitution. Doesn't that look like a trig substitution? But that's why I see how these are related. A lot of these were, this table of performance here, when a lot of these were produced by using those integration methods, like doing the trig substitutions, like in section 7.3. So if you wanted to play around with a problem like that again. That's what they mean by using a table of integrals. Now you can go in there and go, okay, but notice it wasn't a fast problem, was it? Because these were not the same originally. I had to kind of manipulate that, didn't I? But we did. We did. We were able to do that. Hey, any questions on that stuff? Oh, great, Dave.
For exams, is there any special section you want to say section 2 or should we just?
Great question. For this section here, once again, it's like You gotta memorize all these, right? No, right? You don't memorize. But what it is, like, one of the options is, okay, you give students this, and then you give them a problem like from that section, you go, you're gonna have to look through all these to figure out which formula you gotta use. That's great if you got like tons of time to sit here and look. Let me see if I can recognize that one. They kind of label them each one. My preference when I do that is to actually start a problem just like this. Use this right here to solve that problem. In the practice problems that I gave to you, I put like 4 of them. So it's not something, I don't want you to go crazy with. This section's kind of light compared to the other ones. Because it's like, oh, they're giving us a cool formula. You might have to do a little manipulation when you get it going. That's what you'll find. Okay? But great question. So that way, you wouldn't have to what? You wouldn't even bring this thing in. But feel free to have this because it's something it's interesting just to look at. I mean, how many pages long is this? This is 5 pages? Yeah. So very good. But that's how I like to put for that problem. I mean, that's how I like to assign the problems in terms for a test. So you know exactly what to expect. It's like he would give it to me and actually have me set it up. But it requires some kind of manipulation. Sound good? If you can do the 4 practice problems that I put for Simon, you're good to go. Any other questions? Doing a great job today. Have a super weekend.